Hi there, I call this lesson Trig Day 1. And that's because I'm not referencing the textbook just because I go a little bit out of order from the textbook. In this lesson, we are going to be doing some review from geometry and also Algebra 2 Advanced, where we're going to be deriving the unit circle and then talking about how we can use the unit circle as a reference for evaluating trig functions. So there's 6 trig functions: sine, cosine, tangent, cosecant, secant, and cotangent. And we're going to, you guys have in geometry used SOHCAHTOA, right? So the ratios of the sides of the right triangles in order to evaluate the trig functions for some angles, or to determine what the values of the trig functions are based on some given information. And then in Algebra 2 Advanced, you guys were introduced to the unit circle and how to use that as a reference for evaluating the trig functions for angles that are on the unit circle. So here we go. And some things I'm saying I'm not explaining in depth because I'm assuming it's review and I'm expecting that you know. So let's first look at the definition of similar triangles. So similar refers to the triangles being identical in shape but not necessarily size. And similar triangles have equal corresponding angle measures. So like if these two triangles were similar triangles, you could think of like me using the notability feature where I just resize that first triangle and shrink it down a little bit. That would mean that this angle would be equal to this angle. This angle would be equal to this angle. This angle would be equal to this angle. And if I name the sides of the triangle, so how about A, B, C, D, E, F. Now, side A is not equal to side D, right? They are in the same position on the triangle, but they're different side lengths. But there is a relationship between the side lengths or the ratios of the sides of triangles that are known to be similar. So, for example, if we took the ratio A over C, that would be equal to, from the second triangle, D over F. Or if we took the ratio from the first triangle, C over B, that would be equal to, from the second triangle, F over E. And so on. We are going to focus on similar right triangles. And right triangles are triangles that have an angle equal to 90 degrees, right? We call the 90 degrees a right angle. And for the sides of a right triangle, the two sides that create the 90-degree angle are referred to as the legs of the triangle. And then the side opposite the 90-degree angle is referred to as the hypotenuse. So there are two special right triangles that are going to be helpful to us. And we're going to derive the relationship between their side lengths. Or basically come up with how you can determine what the side lengths are for any triangle that has the angle 30, 60, 90, right? They represent a set of similar triangles. Like there's infinitely many triangles that have the angles 30, 60, 90, and infinitely many triangles that have the angles 45, 45, 90, but their side lengths have a special relationship. So to derive the side lengths of a 30, 60, 90 triangle, I'm going to actually start with an equilateral triangle. And you guys hopefully remember that an equilateral triangle is a triangle that has equal side lengths. And remember, the angles for a triangle should sum to 180 degrees. So if they have equal side lengths, we're going to take 180 degrees and just divide it by 3. So each angle here would be 60 degrees. And then I'm going to name the sides, each side 2x. You'll see why I choose to do that, right? They're all just equal in length. So now I'm going to create two right triangles by dropping a perpendicular, so cutting that top angle in half, right, and forming two right angles. And then we're going to just focus in, we've created two right triangles, we're going to focus just on one of the right triangles. So I'm going to draw that down here. That didn't work out so well. Here, let me try again. There we go. Okay, so let's say that's just that triangle that I highlighted. This angle would be 60 degrees. This top angle would have been cut in half, so this angle would be 30 degrees. And then we have the right angle of 90 degrees. The hypotenuse of this right triangle would be 2x. And then we cut that bottom side in half. So that bottom, the side opposite 30 degrees would be equal to a length of x. And we don't know what the other leg is. So I'm gonna call it question mark. But you guys should remember the handy dandy Pythagorean theorem, what that says about the relationship between the sides of a right triangle. So Pythagorean theorem says a squared plus b squared equals c squared. What are a, b, and c? So a and b are the legs of the right triangle. And then c is the hypotenuse. So referencing our Pythagorean theorem, in order to figure out what this remaining side is, we would have question mark squared plus x squared equals to 2x squared. The right-hand side there would simplify to be 4x squared. Okay, and then remember, we're solving for a side length. So whatever the side is, it's going to be positive. So we would normally want to put plus or minus the square root of 3x squared, but because it's a side length, we only need to worry about the positive value. And then that would simplify again. X represents a side length, so it's going to be positive. So we don't need to put root 3 times absolute value of x. We can just put root 3 times x. So this side is equal to root 3 times x. Here, just for reference. Okay, so then let's look at the 45 90-degree triangles. And we know for that triangle, we would have our right angles. And then these other two angles, which remember have to be complementary angles, they have to add up to 90 degrees, would each be 45 degrees. And the legs would have to be equal in length, right? Because they're opposite the same angles. And we want to figure out what the hypotenuse would be. So again, using Pythagorean theorem, that would be x squared plus x squared equals to question mark squared. The left-hand side in that equation simplifies to be 2x squared. And then again, we're solving for a side length, so we only need to take the positive. And that would simplify to be root 2 times x, or root 2x. All right, the reason we did that, we want to fill in our unit circle. This probably looks familiar to you. So this is a unit circle because it's a circle that is in the XY plane. So I'm going to make this look a little bit more like it's in the XY plane just by extending the lines here. Okay, so the very center is the origin. This horizontal line is the x-axis, and this vertical line represents the y-axis. So a unit circle is a circle that is centered at the origin and has a radius equal to 1. And the equation that actually represents the unit circle is x squared plus y squared equals to 1. And knowing that this is a unit circle, I'm able to fill in some of the points that lie on the unit circle here. Like this would be 1, 0. So it would be 0, 1, negative 1, 0, and 0, negative 1. And you can see the degree symbol. So these lines here are all going to represent the positive angle that you can think of as the angle starting on the positive x-axis and then rotating counterclockwise. So like that first angle is actually going to be, well, actually the first angle is going to be 0 degrees. And then in quadrant 1, that would be 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And we're going to focus just on quadrant 1 to help us with filling in the entire unit circle. So I'm going to label the quadrants just as a reminder. Okay, so we're going to focus in on quadrant 1. And notice those angles are the angles from those special right triangles that we just derived the side lengths for. So if I think about drawing a right triangle in quadrant 1 here, right, where I have the right angle, this angle here would be the 30 degrees, meaning the angle up here would be 60 degrees. Now, this triangle, the hypotenuse ends up corresponding to the radius of the circle. And we already said this is a unit circle. It has a radius of 1, right? This value has to be 1. That length has to be 1. So let's go back up to where we derived the side lengths. And let's think about what would x need to be in order for the hypotenuse here to be equal to 1. And the answer is x would have to be equal to 1/2, meaning the side opposite 60 degrees would end up being √3/2, and the side opposite 30 degrees would be equal to 1/2. So let's go fill that in on the unit circle. Right, so our hypotenuse is 1. The side opposite 30 degrees would be 1/2. The side opposite 60 degrees would be √3/2. So this point that lies on the unit circle would be equal to √3/2, 1/2. Right, that point that lies on the unit circle. Okay, then moving on, let's draw a 45, 45, 90 degree triangle. Wondering if it would be easier to get rid of my 30, 60, 90 triangle, but we'll try and leave it. Okay, there's the right angle. That means that this angle here would be 45 degrees. This angle is also 45 degrees. The hypotenuse would have to be equal to 1. So we need to figure out what the legs would be if the hypotenuse is equal to 1. Well, to make the hypotenuse equal to 1, x would have to be 1/√2, which would make each of these legs 1 over root 2. We like to rationalize the denominator, meaning make the denominator into a rational number because root 2 is not a rational number. And we do that by multiplying by root 2 over root 2, which is root 2 over 2. So the legs of the triangle are going to be root 2 over 2, both of them. Meaning this point on the unit circle would be root 2 over 2, comma, root 2 over 2. All right, and then kind of rotating the 30, 60, 90 triangle, right? This would be 90 degrees. This angle would be 60 degrees, meaning this top one would be 30 degrees. Hypotenuse is 1, so we would just be switching the legs, right? So this side would be 1/2, this side would be root 3 over 2. So this point would be 1/2, comma, root 3 over 2. And then we can just use symmetry to help us fill in the other points around the unit circle. So like we would have negative 1/2, comma, root 3 over 2, negative root 2 over 2, root 2 over 2, negative root 3 over 2, 1, comma, 1/2, and then reflecting over the x-axis, that would be negative root 3 over 2, comma, negative 1/2, negative root 2 over 2, comma, negative root 2 over 2, negative 1/2, comma, negative root 3 over 2. And then you can think about those points from quadrant 1 being reflected over the x-axis, or the points from quadrant 3 being rotated over the y-axis. But then we have 1/2, comma, negative root 3 over 2, root 2 over 2, comma, negative root 2 over 2, and then root 3 over 2, comma, negative 1/2. Okay, we're almost done. We also need to fill in the angles. So we have the angles from quadrant 1. And if you notice, right, so this first angle was 90 degrees. And then if you keep adding 30 degrees, we'll be able to fill in a bunch of the other angles. Oops, not that one. Most of the other angles. Right. So we'll do that. So if I add 30 degrees to 90 degrees, that's 120 degrees, then 150 degrees, 180 degrees. And the other lines that are there are for the angles in radians, and we're going to do that in a later lesson. 210 degrees, 240 degrees, 270 degrees, 300 degrees, 330 degrees, and as I'm sure most of you know, 360 degrees is a full rotation. And then we can fill in those remaining angles by taking, if we think about starting at 45 and adding 45 degrees. Oh, I missed the 180, right? If we just keep adding 45 degrees. So you can think 90 plus 45 degrees, or the difference between 30 and 45 degrees is 15, so you could just think about adding 15 degrees to like 120 degrees, which would be 135 degrees. This would be, 225 and 350, why do I keep writing 1? 315 degrees. Okay, Okay. And so if you remember SOHCAHTOA from right triangle trig in geometry, right? It was a way for you to remember what the ratios that sine, cosine, and tangent were equal to. So their inputs are angles, and then the outputs were the sides, the ratios of sides of right triangles. So that's sine of, I'm going to use theta, right? Theta, Greek letters are common to use as variables to represent angles. You could use any variable really to represent the input there. But the angle is the input, and then the output is the ratio opposite over hypotenuse. So the side opposite in the right triangle from the angle theta over the hypotenuse. Okay, ka is for cosine. So cosine of theta equals to adjacent, the side next to the angle theta over hypotenuse. And then TOA, that's tangent of theta equals to opposite over adjacent. And I'm trying to think. What do I want to do first? Okay, so just an example, like if we thought about using one of the angles from our special right triangles. So like if we wanted to determine what cosine of 30 degrees is, we could go up to that triangle. Okay, so we focus in on 30 degrees. Cosine is adjacent over hypotenuse. So the side adjacent would be root 3x, and then the hypotenuse would be 2x. Well, root 3x over 2x, the x's would cancel every time. And so cosine of 30 degrees would be equal to root 3 over 2. And if I wanted to take sine of 30 degrees, can go up to the same triangle. Again, focusing on 30 degrees. Sine is opposite over hypotenuse. X over 2x, which would simplify to be just 1/2, right? Because the x's cancel. And how about tangent of 30 degrees? Opposite over adjacent. So, right, TOA. Opposite over adjacent. X over root 3x. Well, that would simplify to be 1 over root 3. But remember, we want to rationalize the denominator. So if you think about multiplying by root 3 over root 3, that gives you root 3 over 3. You may notice, or you might have noticed, or you might remember from learning this before, that, okay, so for 30 degrees, so look at 30 degrees on your unit circle. The x-coordinate at the point that lies on the unit circle is equal to root 3 over 2. And the y-coordinate is equal to 1/2. Well, this isn't a coincidence. On the unit circle, because the radius is equal to 1, and that radius corresponds to the hypotenuse of those right triangles. The x coordinate here, so on the unit circle, The x-coordinate, this is only for on the unit circle. So the x-coordinate will end up corresponding to cosine of theta. So cosine of whatever the angle is. And the y-coordinate will end up corresponding to sine theta. So we can use the unit circle as a reference. Like if we wanted to determine what cosine of 60 degrees is, we could go to the unit circle and go, okay, well the x-coordinate at 60 degrees is 1/2. So cosine of 60 degrees would be equal to 1/2. And this, now we have angles that go beyond like what are possible in a right triangle, right? So like if we wanted to determine what sine of 150 degrees is, we would go to 150 degrees and look at the y-coordinate, which would be 1/2. So sine of 150 degrees would be equal to 1/2. The last thing that I want you, besides angles in radian measure, which we will get there, the last thing I want you to be able to fill in after having completed this lesson would be the values of tangent. And if you're looking at just even SOHCAHTOA, you notice that tangent theta is equal to opposite over adjacent. Well, notice that there's a hypotenuse and a hypotenuse, right, for sine and cosine. So if we take tangent, and we could also figure this out by, like, if I had you use SOHCAHTOA to find tangent for 30 degrees, 60 degrees, 45 degrees. And then you would notice like, oh, hey, ends up being the ratio of sine over cosine. So tangent of theta is equal to the ratio of sine theta over cosine theta. And notice, like, if we're referencing SOHCAHTOA, that would be opposite over hypotenuse divided by adjacent over hypotenuse, where the hypotenuses would end up canceling, right? Leaving you with opposite over adjacent. What will be helpful for you on the unit circle is that since tangent is equal to sine, the ratio of sine over cosine, move this over because this is only true for, or this is true for on the unit circle, but it will be for beyond too. Then tangent would be equal to the ratio of y over x. So we can actually go ahead and for all of the angles that are on the unit circle, we could also fill in the values of tangent. So y over x at 0 degrees would be 0 over 1, which is just 0. So in orange, I'm filling in the values of tangent. 1/2 divided by root 3 over 2 would end up being root 3 over 3. Yeah, because it would be 1 over root 3, which is root 3 over 3. So I'm just going to write that as root 3 over 3. And then root 2 over 2 over root 2 over 2 would be 1. And root 3 over 2 divided by 1/2 would just be equal to root 3. And 1 over 0 is undefined. Okay, and we can use symmetry, but then you also have to pay attention to the signs, or we could just continue taking those ratios, right? So using symmetry, but you can see that since the x-coordinates are negative, this is going at 120 degrees, tangent will be negative root 3. At 135 degrees, tangent will be negative 1. At 150 degrees, tangent will be negative root 3 over 3. 0 at 180 degrees. And then since x and y are both negative, and negative divided by a negative is a positive, in quadrant 3, we'll have root 3 over 3 for tangent of 210 degrees. 1 for tangent of 225 degrees. Tangent of 240 degrees will be root 3. Undefined at 270 degrees. And then back to negative, since now the y-coordinates are negative. So negative root 3 for tangent of 300 degrees. Tangent of 315 degrees would be negative 1. Tangent of 330 degrees would be negative root 3 over 3. And tangent of 360 degrees would be the same as tangent of 0 degrees, which is just 0. So in orange, I have all the values of tangent. What I have filled in here, so all of the angles in degrees, all of the points that lie on the unit circle that correspond to those angle measurements, as well as the values of tangent, you should have memorized. And you should be able to get to the point where you just visualize the unit circle and referencing it. Because you need to, especially like going forward next year, like you need to be very fast with evaluating the trig functions for any of the angles that are on the unit circle. It will be such a small part of the problem that you need to be very fast, and you shouldn't have to draw out the unit circle or like look at a picture of it. You should have it memorized and be able to visualize. Okay, sine of 225 degrees. Well, it's quadrant 3. Picture it, okay, negative root 2 over 2. And then, so that's the last that I have for a Trig Day 1 lesson. This is looking ahead. This is what we're going to be talking about in Trig Day 2, is thinking instead of the trig functions as being ratios of just sides of right triangles, so just using SOHCAHTOA, what the ratios, the outputs of all 6 trig functions are in the Cartesian plane. So in the